Hello everyone, we are from Group 5 and we are going to present the topic of humidification and its application. So what is humidification? Humidification is a process in which the moisture or water vapor or humidity is added to the air without changing its dry bulb temperature. Why is humidification important? It is important to control air properties in industrial, ensures product quality in industries, and also improves comfort and health in indoor environments. Some of the key concepts for this topic are dry bulb temperature, wet bulb temperature, dew point temperature, humidity ratio, relative humidity, enthalpy, specific volume, vapor pressure, and also saturation curve. There are two main types of humidification process which are adiabatic and non-adiabatic. For adiabatic process, it means that there is no heat added during humidification. It means Q will equal to 0. While for non-adiabatic, there is heat added, so Q will not equal to 0. So for this part, we will be talking about humidity chart. What is humidity chart? So basically, humidity chart, or also known as psychrometric chart, is a graphical tool showing the relationship between those key concepts we said earlier. Why we use it? We use it to determine air properties at any point and also to visualize humidification, cooling, heating, and also dehumidification processes. Listed here is the step on how to use a humidity chart. So first, we can locate the dry bulb temperature. We can look along the bottom horizontal axis of the chart. Next, we can locate the humidity ratio. It can be found on the right vertical axis. You guys can see it. I already highlighted it with a blue color highlight so you can see it clearer. Next, we can locate the uppermost curved line on the chart to find the saturation curve. For the fourth step, we can identify the relative humidity curve just by following the interior curved lines on the humidity chart. Next, to locate the dew point line, we can just look at the vertical line labeled as dew point on the right side of the chart. Right next to it is the vapor pressure line. As you can see in the picture, I already highlighted two different love lines to show the differences between them two. Next, identify the diagonal lines throughout the chart to locate the specific volume. We can also find the diagonal enthalpy scale at the chart to determine its enthalpy. When solving a problem involving a psychrometric chart, we only need two measurements to read the charge. As for this example, it is given that dry bulb temperature is 70 degrees Fahrenheit and the dew point temperature is 50 degrees Fahrenheit. So we can locate both of these values at the charge and point them first. Once you have marked the point where your known measurements intersect, you can use a ruler to gather information about the dew point, relative humidity, specific volume, enthalpy, and also vapor pressure. Just follow the lines extending from the point of intersection to the various scales on the chart.
As we can see, the equation has two parts, which is Z is equal to Hg and Ng. Hg usually depends on the gas, feed gas flow rate, or the air, whilst the Ng is to be determined using graphical methods. For the first step of design, we need to know the entering conditions of the tower. In this case, the temperature of the dry bulb and the wet bulb of the entering air is known, so we can use the humidity chart to obtain the humidity value. The humidity value is then used to obtain the enthalpy value of the entering air, and that from the known entering enthalpy value of air, we can use it to determine the exiting value of air using the heat balance equation, which is equation 10.52. Using the given equilibrium data and operating conditions, we can use those values to plot the equilibrium line and the operating line inside HY versus T graph. To obtain the interface enthalpy values, we need to use the slope value to plot a line or several lines that connect the operating line and equilibrium line. Another more common method is to use the XY guesstimate. To use the XY guesstimate, we need to table out the values of TL and HY, which is obtained from the operating line, and then we set amount of X1, which is each amount of X value of temperature but less. A value will be determined from the slope value with the equation beside it. The points from the operating line and X1, Y1 will be connected, and then when that line intersects the equilibrium line, that will be your HYI value. To determine Ng, the two calculated parameters is then plotted or is used as data to obtain the area under the graph. Now the area under the graph is representative of the integration that is shown on the equation. Finally, the ng value would be resubstituted into the initial equation with Hg.
So here is the calculations for water cooling tower by using the overall mass transfer coefficients. So the formula is actually quite similar to the film method. So first we determine the Hy from the humidity chart, and then next we calculate the Hy1. Then we calculate Hy2 by substituting the Hy1 that we calculated just now into another formula. And then we plot the equilibrium line. Then we draw the operating line using the point TL1Hy1 and TL2Hy2. Next, we need to plot several vertical lines by using the Hy value, and then we extend the line until it touches the equilibrium line like what I have shown using the red lines. And we need to plot at least 5 lines. Then, from that we can know the Hy stars. Next, we can tabulate the values in this table. So for B column, the green color box is actually we can assume the value by ourselves by drawing the vertical line from the operating line to the equilibrium line. And then for the column C and D, the blue color box is actually the value that we can read from the graph. And then after completing 3 B, C, D columns, then we can proceed to E, F, G for the calculations. And then for the G column, it's actually we have to find the area for each segment. And then we summarize all each segment, we can get the total area. Actually, from the calculation just now for summation of all the above value for the area of each segment, actually is straight away the answer for the calculation for the integration part for 1 over Hy star minus Hy. So we can straight away substituting the value into the Z formula. Z equals to G over MB KGA times B, and straight away multiple with the value that we calculated for sum in G. So we no need to do the integration part, and then we can get the value of Z.
So we are going to learn how to solve the problem if the value of gas inlet flow rate, which is G, is not given. So the first operating line if G is given would be TL1 and Hy1, and the second operating point will be TL2 and Hy2, and their slope will be LCL over G. But when only G min is given, we have to use 2 steps to solve it. First step is to draw the operating line for G min to intercept the equilibrium line at TL2, then read Hy2 max from the graph. Next step is to calculate G min or L over G min. Then we can calculate the value of G. As we can see in the graph, combines 2 operating lines in it, where the first one is with slope LCL over G and the second one is with slope LCL over G min. So the Hy2 max for G min would be at point N, but you have to remember that point N must intercept at TL2, but point N not necessarily need to intercept at equilibrium. There are 2 conditions to construct the operating line of G min. The first condition is where point N show the intercept at both line TL2 and equilibrium line. So the operating line for G min can be connected between point M and point N. In the second condition, we can see that the operating line for G min cross over the equilibrium line and part of it are above the equilibrium line, which is not the right way to sketch operating line. The above graph is the wrong interpretation for operating line of G min. The below graph is the right interpretation because the point N intercept at TL2 and not crossing but tangent to the equilibrium line. So there are 2 conditions in this procedure. And the first condition, we have to plot point M. Then we plot the equilibrium line on the Hy and TL graph. After that, we draw the vertical line with S equal to TL2. Next, from the point M, we draw a straight line to intercept the equilibrium line at TL2, which is for point N. Then we have to obtain the value of Hy2 max. After that, we calculate the G min and G value. And afterwards, we have to calculate Hy2 and draw the operating line for G. For the second condition, the first 3 steps are the same as the first condition step. And then we from point M draw a tangent to the equilibrium line until it intercepts at axis TL2 which is at point N. After that, we have to obtain the value of Hy2 max. The Hy2 max value, we must remember to not get overestimated value for the second condition. And next, we have to calculate G min and G. Lastly, after we calculate the Hy2, we have to draw the operating line for G. So as a summary, for humidification process, the operating lines always lies below the equilibrium line. The temperature of water are getting lower in humidification and humidified the air as water content flow into the gas phase. For dehumidification, however, it is the opposite of humidification, as its operating line lies above the equilibrium line. So as the moisture is being removed from the air, the humidity and also temperature of air are also getting reduced. Applications of humidification can be found in most major industries such as healthcare, food industry and textile industry. So for healthcare industry, humidification are being utilized within HVAC system. So what does HVAC stands for? HVAC stands for heating, ventilation and air conditioning. This system protects the patients, staff and equipment by controlling the temperature and airflow. They combine heating to warm and ventilation to refresh and also air conditioning to cool and dehumidify. Modern setups use a central AC, humidifier, furnace, ducts and fans, which are all managed by a thermostat that adjusts automatically to room conditions. So last but not least, application of humidification can also be found in textile industry as well. In the textile industry, maintaining the right humidity is essential for both product quality and production efficiency. When humidity levels drop too low, fibers become brittle, leading to increased yarn breakage, static electricity and also machine downtime. This not only affects fabric quality but also slows down production. To prevent this, many textile facilities use industrial humidifiers to maintain optimal relative humidity, typically around 60 to 70%. This keeps the fibers flexible, reduces the static build-up, and ensures smoother weaving and spinning processes.